Today we are starting chapter 10, which is looking at circles. So we start off with some basics in circles and our essential question: what are the definitions of the lines and segments that intersect a circle? When we define a circle, we say it's the set of all points in a plane equidistant from a given point. We say in a plane because if we go in three-dimensional space, this would be a sphere. The set of all points in space is a sphere. That given point, you're probably already familiar with, is the center, right? And that distance would be our radius, which is our next two terms. So when we define the center, we just say the point from which all points of the circle are equidistant. When we name a center, we would just use a point. When we name the circle, we use the center point. So if we're calling this center here, if we say that point is O, then our circle here would be circle with a dot in it, A. All right, and that would be if this point here was A, that's my center. That's how we name our circle. So our circles are named based on the center. Okay. The radius not making sense. All right, the radius is I have something different on my paper I'm referencing, so this might not be 100% definition, but it fits what we're doing, is the distance from the center to the edge of the circle. That will always be a line segment. So if we say the center is O, or I'm sorry, the center is A, we'll call this point out here, actually I'll call this point out here B. So a radius would be AB with the bar over it. Okay. A chord is a segment whose endpoints are on the circle. This one is probably new. So if you look at the picture, they show a chord here. We have a point here. We have a point here. Those are both on the circle. Okay, so that is a chord. Okay. Our diameter, which you should be familiar with, is a chord that contains the center of the circle. Okay. So the diameter here is a chord because it touches here, and it goes through the center, which makes that chord a diameter. Okay. The next two are probably new as well. Secant is a line that intersects the circle in 2 points. We show a secant here in this picture. The difference with the secant and the chord is the chord stops. The secant doesn't, which is why here we have a line and here we have a segment. Right? So if this chord would continue here, it would be a secant. Here, if this stopped at the corners, it would be a chord. right? So if we look at this point, we'll say this is C and this is D, right? CD, the line segment, is a chord. CD, the line, is a secant. And then our last term here is tangent. Tangent here is completely different than trig functions. It's not at all related to trig functions. A tangent, when we're referring to circles, is a line in the plane of a circle that intersects a circle in exactly one point. Right. So here we have a tangent. It touches at B. We need a second letter on there so we could name that. The point where it touches is the point of tangency. The line just touches. Okay. The reason it says in the plane is I don't want something like the pen coming down here and touching at that point. That's not in the same plane, so that would not be a tangent line. Tangent line has to be in the same thing. And also it doesn't have to be a line, but you have to consider the line. If I draw a line here that stops, if the line continued, it would go in the circle. So that doesn't work, right? So a tangent line just touches the circle, right? So that example 1 here asks us to identify different things, right? Tell whether it's a line. Tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent. So EA, here, we start at E, we go up to A. That starts on the circle, but it leaves the circle, okay, and touches the circle in more than one spot. That would make it a secant. BC, also know that is a radius. And then DE comes here. That just touches at B, so DE is a tangent. Okay. Just pointing out some other things. BA would be a diameter because it is a chord that goes through the center. AF would be a chord. Right. B would be the point of tangency. Right. Example 2, all right, looking at these lengths, I have circle A, so I have the center of that. So realize that means that is the center of this circle. When it says radius of circle A, this is the center, this is the circle. When it comes down here, B, this is the center, this is the circle. Okay, so radius, I just count 1, 2, I have a radius of 2. Diameter, I can count, but I should know that's double, so that's 4. When I come to B, come over 1, 2, 3, 4. All right, and again, diameter I could count as well. Count up or down, count across, but that should be double, which is 8. Okay. Now the top here, it talks about points of tangency. Right, and tangent lines. So circles that touch, right? So you have the circles here overlap. The circles here touch at one point. Okay, so those are tangent circles, right? Here we have no intersections. Here we have concentric circles, meaning they have the same center. Right, so tangent circles touch at only one point. Concentric circles have the same center. We'll see those terms come up some. What we look at more is how many tangent lines a pair of circles has. Okay, so we have 2 types of tangent lines. We have internally tangent lines and externally tangent lines. Really simple. Internally tangent lines go in between the circles. So this line here is internally tangent. Okay, external tangent lines don't go in between the circles. This is a little hard to tell, but this one is externally tangent. Okay, so these circles here in example 3, it says tell how many common tangents they have. That would be 3 common tangents. You have the one in between them, all right, and then you have one on the outside on this side and one on the outside here. Okay. Again, tangent circles can only touch the circle in one spot. So some of these, when you draw them, look like they touch it more than one spot, but basically we're saying the circles just touch in one spot. This touches in one spot as well. All right, so we have 2 external, 1 internal. In the second one, we don't have any internal because our circles overlap. So all we can have here is 2, where we have them on the outside. And the last one, similar to this picture here, we have 1. Okay. These will always fall between 0 and 4. 0 would be circles where one is inside the other. You can't have a tangent to both circles because once I touch this circle, I'm inside the other circle. The max I can have is 4, which would be in a picture like this. You'd have 2 in between, that would come like this, and you'd have 2 on the outside, like we see on these 2. So the maximum number of common tangents I can have is 4. The minimum number is 0. Okay, so then we have a theorem here. In a plane, a line tangent to a circle, a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle at the endpoint. Okay, so here I have a radius, I have a line, they show me the 90 degrees. So since this is a radius, I know that is a tangent. One of the things we use with this is Pythagorean theorem, right? So if I look at example 4, all right, this is where my 90 degrees should be if it works. So if I do 10 squared plus 24 squared and see if that's equal to 26 squared, if it is, then this is a tangent. Okay, so here I have 100 plus 576 equals 676. Those 2 are equal. So my answer here would be yes. All right. Example 5 has some weird math in it that we haven't been using a lot of. It's probably beneficial to see, especially if you're planning on moving along in higher level math classes. But I'm going to save that one to the end and get through everything. Here we have 2 other things to look at before we look at that. So the external tangents congruence theorem says tangent segments from a common external point are congruent. Okay, so if I look here, RS and ST are from the same point, they're tangent to the same circle, and therefore they have to be congruent. So when I'm looking at this problem, right, these are tangent from the same line, so 28 is equal to 3x plus 4, 24 is equal to 3x, and x is 8. All right. Looking at example 5, going back up there, all right, what makes this difficult is this line here that has the 49 and the r on it. So when I'm trying to find r, I have 77 squared plus r squared. That's this and this. That's my a and my b. Then I need to square 49 plus r, the quantity squared. Right? So the one side is easy. We get r squared plus 5929. I switched where those were there. This goes with the 77. This goes with the r. This, depending on how much you know, you can do that fairly simply. But basically, what I'm doing is I'm doing 49 plus r times 49 plus r. So I'm not just squaring the parts. I need to do 49 times 49. I need to do r times r. But I also need to do this 49 times this r, this 49 times that r, which you're probably familiar with as FOIL. I'm doing the firsts, the outers, the lasts, I did that out of order, and the inners, which would be these 2. Right? So when I multiply that out, right, we get r squared plus 5929 equals 2,401 from the 49s. I have r times 49 twice, which is both 49r. That gives me 98r plus r squared. Okay. The nice thing about this problem is these r squareds cancel. So now I'm just solving this nice problem with r there. Right? But it's normally the foiling there that will mess people up. So we'll continue that over here. I have 5929 equals 2401 plus 98r. So 3,528 equals 98r. When I subtract the 2,401, divide by the 98, and I get 36r. Or my radius here is 36. Okay, and that is our, put that there so you can see it a bit, move it a little bit. And that is our basic information on circles.